Все, я слайды прямо здесь буду в скайпе видеть, да, или как?
Да?
Ага, окей.
Hey, hello everyone. If you
Hello.
can see us, if you can hear us, please set the thumbs up in the YouTube chat so we will know we can start. Today we have an exciting topic to talk about, and we have a special guest from Russia, Dmitry Astankov, data scientist, who will
Hi.
help us to get deeper into the machine learning world. Hey, hi Miriam, hi Ravi, hi Ronald, Naresh. Amazing to see you here. Chase asks, are we meeting on YouTube and Zoom at the same time or just YouTube? YouTube is the primary place for us to meet, and you can ask your questions in YouTube chat, and we will do our best to answer them. Hi, Konstantin. I see some familiar names already in the YouTube chat. That's great. And looks like sound is good, video is good, and we can start. We are going to cover a lot of amazing things today. And not only we will be speaking, but also you will be pushing buttons because it's a workshop and there is nothing better than learning and forced by the practical lab. Let's go and let's do it for all of us step by step. So first things first. It's DataStax Monday Learning, special program with special guests delivered to you by DataStax developers. Our goal is to talk to you about the most important topics in informational technologies, software development, and all the related things from engineers to engineers, no marketing bullshit, absolutely free. And we're here to make this practical also as much as possible. Good. Yes, Andrea, there is a GitHub for this course. That's not exactly the course, but just an introductional workshop, and I will give you the link very soon. Now, if you will like this workshop, mostly probably you will like our other workshops. Today we have Intro to Machine Learning. This Wednesday we're building a multiplayer game with real-time interactions using event streaming. And next week, we are going to get closer look at Spring Web Flux and NoSQL databases in our build and appointment scheduling app workshop next Wednesday. Good. So, and today this is Introduction to Machine Learning with Apache Cassandra and Apache Spark, delivered to you by Aleksandr VOLOCHNEV and Dmitry Astankov. Thank you very much for watching. Let's start.
Pleasure.
2 words about myself. I'm developer advocate lead at DataStax, cloud architect, and big fan of each and every new technology which makes this world a better place. And of course, machine learning in no way could have escaped my attention. But you know what? I'm not a professional data scientist. I have a little bit different specialization. So today with me, Dmitry Astankov. Dmitry, could you please say a word about yourself?
Yeah, sure. Thank you. Hello, everyone. It's very nice to, well, not see you, but feel your presence. And I'm a data scientist at Akvolon company. That's the general idea of it. I'm probably not a very not working very long as a data scientist, but still I'm interested in this area for what 2.5 years now. So I can probably know a thing or two about this thing.
Yes, great. And Miriam asks us, is DataStax based in Germany? DataStax is remote native, so it's based everywhere, including Germany, Australia, France, Italy, but our headquarters are in the United States, Santa Clara. So let's move on. A little bit of housekeeping so you will understand how this workshop works. First of all, streaming. We have mainstream, primary stream. You mostly probably watch us there right now on YouTube, of course. And we have plan B. If something goes wrong with YouTube, we can switch to Twitch. Twitch, we are hosted as DataStax developers, but primary platform is YouTube. Then, You can ask your questions on YouTube chat, but you know what? As long as stream is over, it's all gone and you cannot communicate with us anymore, and we don't like it. We like to communicate and talk to you. So we have a dedicated Discord server, DataStax developers, and we can talk regarding this workshop even after, when tomorrow, next week, next month, when the workshop is over, we still will be there, at least me. Then, for the materials, everything is published on GitHub, and of course, everything stays available to you forever, as long as GitHub exists. I hope it will be quite a long time. And finally, for the runtime for today lab practical part, we will use Cassandra as a data storage, Spark as a, let's say, machine learning platform for us for today, and or parallel computations platform, better to say, and a little bit of Python. Yep. Framework, yeah, better call it framework. And Python as a programming language. But if you are not familiar with Python, don't worry, it's all prepared and it's all well explained. So you don't have to be a Python expert. It's completely fine to be a beginner. As long as you understand any programming language, you will be fine with our lab. Then let's move on. To do the practical part, to do the lab, you have two options. If you have Docker and if you have Docker Compose, you can do it using your own laptop or computer or whatever you prefer. And it's a great one because you can do it today or tomorrow or after a week later. Wherever you have time, it will be good enough. But if you cannot install Docker or whatever, for whatever reason, but you still want to do the lab, that's amazing because we have you covered. We have cloud instance launched for you. And if you will decide to do a lab after the session, you will contact me. I will give you the contacts later on. And I will create a cloud machine for you to do the exercises to run the lab. Don't worry. We can make it. So, okay, for local setup, you will need Docker and Docker Compose. Please first watch us doing those exercises. Don't rush. You will have enough time to do it later on your own. And for cloud setup, please contact me to get your cloud training instance. Easiest way to do it is just to contact me using LinkedIn at datastax.io/Alex, or use my formal email address, which is way much longer. So I suggest you to go for LinkedIn. Then we are getting to a very important part, which is the definition. What is machine learning? One of the formal definitions, or maybe not so formal, says as what machine learning is a field of study what gives computers the ability to learn without being explicitly programmed. That is an incredible thing. That's a very nice explanation. Wow, computers learn without explicitly programmed. Amazing. But is that really explains anything? I don't think so. But you know what? If you go to Wikipedia, it won't help you neither, because Wikipedia is like, we have a joke, Wikipedia is useless. If you know what is it, you don't need Wikipedia definition, and if you don't know, it won't help. That's exactly like that for machine learning, because when you start to read, you get lost very soon. Machine learning is a scientific study of algorithms and statistical models what computer systems use to perform blah, blah, blah. No, 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 no. We need something better. I suggest us first to use my own definition, which doesn't explain also a lot, but at least much shorter. Machine learning is a science of drawing circles and colorizing them. Why? You will see in a moment. Dmitry, how would you explain machine learning before we proceed to the next steps?
I personally would go with the first explanation, which was on the first slide, previous one. But probably I've seen a lot of definitions, and this is a problem actually, that there isn't any one single unified definition. And I've heard a lot of them, and probably the best ones are this one, and also the one that the machine learning is a science that studies algorithms where machine learn from experience. But this is probably very close to this explanation, which you can see on the slide.
Yes, good. So when I tried to find the best explanation for you what is a machine learning, I realized that what the best explanation can be only live demo and practical lab, and there is no better way to explain what is it and how it works. Speaking of which, let's take a look from another point of view, not from the formal definition point of view, but from how it works and when it used and when it useful point of view. So let's take a look. How it works. Machine learning is a scientific way to process raw data using algorithms to make better decisions. So what is the raw data in this case? Raw data is mostly probably some rows in your database, and it can be literally everything. Weather reports, yes, very often. Some price reports on stock exchanges, yes, absolutely, all the time. Any kind of data, any value, any change can be a raw data we could use later to process with raw algorithms to help us make better decisions. When we get to the algorithm point of view, what is an algorithm? This question is a little bit harder because, well, there are very many of them, but the general idea of the algorithm will be, Dmitry, how would you define an algorithm per se?
That's the process of projecting our data into our decision or like target label, whatever it is, whatever we want to get.
Yeah. So if we
maybe not the process, but some, what is it? Well, probably process, yes.
Set of steps, or maybe
rules, a set of rules, let's say.
Right. And there are many different algorithms, but the general idea is always the same. You give some raw data for this algorithm to process. You give some property, you set up some properties of this algorithm. There are different. For example, for Kmeans clustering, you may need to define amount of clusters and so on. So every algorithm has some tunable settings you can adjust. And as a result, you may get some classifications or predictions. We will see it in a moment. It must feel now like you are not getting the idea yet, and that's perfectly fine as it's designed. Give us a moment. Yep.
I have just another explanation which might like share some light on the difference between machine learning algorithms and like classical algorithms. It would be better to draw it, but you can easily imagine it in your head. So compared to like classical programming, where we have some data and we have some functions which do like exactly what we like program them to do. And our like goal is to get the output of that function. And in machine learning, what we want to achieve is we want to learn that function. We don't know what it is. So we have data and we have some labels, if we're talking about supervised methods, which we'll discuss later. And we want to learn the underlying function from the data and to use that function, which we learn afterwards on new data. So just yet again, in classical programming, we know the function which we apply, and in machine learning, we don't know them, and we want to learn them.
Yep. So it's more about exploratory methods, let's say. But let's take a look at a thing. What are the use cases for our algorithms? In which fields of human life they are used? First of all, Dmitry, I believe you worked a lot with natural language processing, right?
Yes, and I still do.
Okay, so what is it, natural language processing? What is it about?
Well, in general, this is about processing texts and doing a lot of things with them. Like, for example, a classical example is machine translation and probably some, well, there are a lot of things that I can remember any right now. Well, the classical example is just machine translation, which is like probably first thing that people tried to do with machine learning. One of the first things.
Yeah,
and
of
that
course.
relates to text.
Mm-hmm. From my limited point of view, let's say mostly known use cases, like what will be easier for our attendees, guests today to recognize. First will be obviously translations. Second would be, from my point of view, if you speak to your Alexa or Google Assistant or Siri, your voice should be processed somehow, and some actions should be taken based on that. And that's also natural language processing, because it's a processing
Yes,
of a
but
natural language, right?
yes, but there is one more domain included there, such as automatic speech recognition, and that's somewhere at the side of natural language processing. That's more to speech processing.
Right,
But
right. Hey, you
yeah,
know what?
afterwards, after
Mhm.
you like recognized what is being spoken, then you are moving to the domain of the natural language processing.
Right. So I never thought of that from this point of view, but that's perfectly right. First, we have to convert voice as sound waves into the text, and then natural language processing should already define what the customer wants us to do. Okay, but of course, that's not the only one and only limited use case for the machine learning. When we speak about the forecasts, is it about to be a market price or rating of something or a weather? That's a very common use case for machine learning algorithms. Aberration detection from the whatever field you can imagine. Fraud, yes. Intrusion, yes. Disease, also perfect match. Very common field for machine learning algorithms is a classification. Face recognition, right. Voice recognition, correct. Categorization, yes. Spam detection, very common feature. We will analyze later deeper today with naive Bayes algorithm. But also recommendation, navigation, and many others. Machine learning is no anymore like it's not the just fantastic stories, but it's just the reality, and it's around us everywhere. So, meanwhile, we have a great question in the YouTube chat. Kindly suggest some machine learning articles, books for beginners by Vimalika S. I hope we will do something like that closer to the end of the workshop. But for now, let's move on. We discussed a little bit of the algorithms, but as said, I don't really believe in the just pure theory. Let's take a look at it in the practice. We will take a look at the K-means algorithm, and we will see how it works step by step using a real live demo. So there is an amazing place to play with K-means clustering. I will send the link to the YouTube chat, but I kindly ask you first to take a look on what's going on the screen, and then later try to play with it on your own, okay? So K-means is a clustering algorithm. It's not so much about the categorization, let's say, but it's more about identifying points what relate most to each other, and we will see it in a moment. Take a look. One of the examples I like the most. Imagine you are going to open a pizza restaurant specialized on a delivery. And I don't know how you have the data of all the customers in your city, those have bought once or twice or many times maybe some pizza with delivery. And your city is huge and you have very limited amount of money. You cannot open a dozen of restaurants, of course, right? So you want to find the best locations, best place, so every customer will have his pizza delivered hot and nice, but not too old, not already cold. And using this little lab, we can try to draw some we can try to draw some areas, like, for example, I will take this one as an example. I will add some points and show you how this algorithm works. For now, it's not clear what's going on, but give me a second. I will explain you. Clustering algorithm, K-means clustering algorithm is a thing what tries to categorize or to put into groups, to bring into clusters some points of data you have. And in this case, I have a map of the city with some areas where are my customers living, so I can try to build my restaurant as close to them as possible. And in the beginning, I will use example with 2 clusters. We will talk about that in a moment. In the beginning, we have raw data. This raw data are those points spread over the city map. And we have some central points of those clusters. And there is a fun fact about K-means clustering algorithm. In the beginning, those central points are located absolutely randomly. They can be located like that, but they also can be located like that, or move it absolutely differently. It's not important in the beginning. Then I start to execute this algorithm, but step by step, very slowly. Now take a look what will happen. I make the first step or first iteration. That's better to call them iterations because every iteration is the same logically as the previous one. First one, from the previous position, every central point calculates the distances to the points which it wants to cluster. And it sees what in this direction we have 0 points, but in those directions we have a lot of them, right? So calculating those distances, this point will, our algorithm will try to move this point as closer to the points as possible, and simplifying, like making these distances smaller. And it sees what the vector we have, like it all goes here, but nothing goes here. There is nothing. There is a city border, of course. So we do the first step. You see, central, the blue one and red one, jump to the middle. Because of a vector of this, the vector which will decrease those distances, obviously leading us to the center. Can we say what those points are clustered well enough? Not really, but we did just first iteration. Then we proceeding with that. When we proceed with that, and we do next iteration. How it will work? Exactly like the previous. A K-means clustering algorithm will calculate for each point for this central, is it getting heavier in this direction, or this direction, or this direction? Which point is closer to us, which point is more far away? And the same for the blue one. And we will do the next step. Boom. And just after the 2 steps, by measuring those distances and choosing the vector which will decrease the medium distance for us, we are already getting somewhere. And we still have a huge difference. You see, we can compare for this blue point, we have those points very, very close. Their distance will be minimal. But those points are very far away. Difference between these distances and these distances is very different. And we see what delta position is over 150. I won't explain it for now. I want to keep it simple. But the point is, we see what those points not really belong to this cluster. They are too far away in comparison with those. But if we take this point, they may be better fit because we already have covering their neighbors, and this distance may be smaller. So we make one more step, and now it's included. Here we have a very nice blue cluster. And red cluster, well, it's better than it was before, for sure, but there is a problem. First, let me finish it. We still have some delta position, something not as big as it was before, but quite high. So I will do one more iteration. Boom. And we now see what blue cluster starts to conquer red points here. And it tries to find the points it's closer by, but this one moves to the bottom right. We make again, iteration, again, and now it's over after 11 iterations. Delta position is 0. That is the perfect place for us to find. And here comes one of the biggest limitations and biggest problems of this algorithm you must understand. K means clustering demo. What does K means in this case? K means clusters. And the problem of this algorithm, or maybe feature, I'm not sure if I should call it problem exactly, is what you have to define how many clusters do you need. And why this example looks not so nice. Like here we have a very nice sweet cluster, very good, but this one looks not so nice. Why? Because we brought in the beginning 2 clusters. But take a look what happened if I raise this number and restart the conditions. So I will restart it, and I will pull them again to the side, so you will see all the steps in a better way.
They won't probably be the same now.
Yeah, not exactly the same.
Extra points.
Yeah, but I occasionally pulled some extra points, but I believe still center of mass will be somewhere here. So now we have 3 clusters.
The general picture must be the same.
Yeah, and we go for the first step, and it was exactly the same. We are calculating centers, and on the second step, we see already this purple one is engaged. But take a look at this one. It has a huge center of mass here, also huge center of mass here, but those are much closer. So distances here in general shorter, distances here in general longer. What does that mean for us? It will try to move closer to this point. If I do next step, boom, indeed, blue one jumps to a center of mass for this cluster. And after a couple of more iterations, they successfully divided those points into 3 groups. And what just happened? We just colorized some random circles. That was about the previous definition, what machine learning is about, colorizing circles. And that was a live example of K-means clustering algorithm works by just measuring distances to each and every point and trying to find out the way, the smallest movement, which will lead to making those distances smaller and smaller. So first problem or feature of K-means clustering, we already mentioned it. It very depends on the amount of clusters we put on the screen. And if I do too many of them, I also will have some weird results. And there are some more potential limitations or issues. What would you mention, please?
If you're asking me, then as you already said, the first big problem is that we must have some insights about the number of clusters beforehand, before we start. And the second big problem is that we must, depending on the data and the number of clusters that we take, the initial position of clusters still matters. I remember you said that it doesn't matter, but it matters. And as far as I know, there are no methods to conquer this, like to nowadays. So the initial position of these clusters may lead to these clusters falling into some local minimum and like never converging to some global minimum, which we would like to get to.
Yep, thank you.
So sometimes we would want to run multiple simulations to get what we want.
Perfect. Then that's exactly the point why I invited you. So the point is, allocation of the central points in the beginning is random, but that matters from the point of view what if you execute this algorithm multiple times with multiple different starting points, you may get different results in the end. And one more point I want to mention is, I like to see them traveling. There is a great question by Miriam. What do we exactly want to reach? What our restaurant covers max locations? Why do we have the 2 points? So in general, first, thank you for asking questions, Miriam. That's amazing. Second, our original idea is to find clusters or to find groups of some entities with similar properties. In this case, those are geographical points on the geographical map. But it's not about, that's not only about the maps, let's say. That can be about very many different situations and cases. In this particular example, we want to have, we want to cover the map of our customers to keep delivery time as short as possible for each of them, and meanwhile not overpay for the redundant restaurants. So I can create here 8 clusters and run more and more and more and more moves, and we will see it will work like that, but it's not the perfect distribution. It's just redundant. And I started with 2 clusters just for the example to explain how they will move and how they will divide those points between those 2 clusters. And that's obvious what 2 restaurants actually will be, in this case, bad for all of them from the minimal distance point of view, right? So our cluster count is wrong in this case. And only by adding more clusters, we may find better distribution, or like 4 in our use case, in our example, is the best one. Good. So what was algorithm? One of many, which takes distances, measures them, and tries to move a central point into the direction what will minify, shrink those distances as much as possible. I suggest you to play later with this clustering demo, but so far we have to proceed with others. It's not the only algorithm we have to cover today. Few more points before we start with the lab. There are some important things we have to remember. First, separation of supervised to unsupervised data, or supervised or not supervised, unsupervised algorithms.
Methods.
Yeah, the methods, thank you. There are, algorithm in this case is not the right word. Actually, there is a little bit more of the classifications. Maybe later you could mention something about reinforced learning. But first, let's explain things about the supervised things and unsupervised things. I will take first step with supervised methods. Take a look. Supervised machine learning is, first of all about data is labeled or must be labeled, or better to say, classified, for example. Let's take a look. Data is labeled or must be labeled. What does that mean? Let's take a look at emails. Do you get a lot of spam? I don't know about you. I used to have a lot of spam, but not anymore. What happened? Machine learning happened. Thanks to the advanced ways of machine learning, use it for supervised methods for exactly for email classification if this email is a spam or not. That's called supervised machine learning methods, and it's used when we have to label or classify emails out of a huge amount of data. Then, if this particular bank operation is a fraud or not, like you use it to make all your you use it to use to make all your use it to buy your things all the time in Calgary, Canada, and now quite surprisingly you are trying to execute an operation somewhere in completely different place, although your last operation was just 5 minutes ago in Calgary, and now it's somewhere in another country, in another continent. Is this operation a fraud or not? There are some more cases, but anyway, it's always about the classification. Or, well, not exactly about the classification, but at least data is labeled, and that's very important for us. What is it about?
Another explanation.
Yeah. Yes.
Another explanation will be that we have in supervised methods, we have data and we have the right answers for that data as our target. Because in unsupervised methods, we won't have the right answers.
Yeah. Good side of the supervised methods, they are easy to test. You will see it very soon as we have some data. Like in order for our spam labeling algorithm to work, we first have to mark some previous emails as spam or not spam. And I believe you did it already many times, sending some emails to spam, that's a spam, that's a spam, that's a spam. We weren't just cleaning our email boxes, but we were also helping mail service providers, let's say, to train their models to identify spam from not spam. So we did all this great shared work to help each other to get rid of the spam. Now, about easy to test. As data is labeled, that's easier for us to estimate if our model, the machine learning model we trained, works good or not good. We will explain it in the next slides. Then, what would you say about unsupervised learning?
Well, the data is not labeled here.
Okay, that's quite obvious, but yeah.
Well, that's the general idea behind this group of methods. And this is a quite like a special group where all the methods are based on this assumption that we don't know the labels. And what we want to do with the data is we either want to reduce the dimensionality, or we want to find some anomalies, or we want to like group the elements based on some underlying pattern, which we don't know ourselves, but we want our model to find out. And that's what we've seen in K-means clustering. And well, that's like the general idea behind this group of methods.
Yep. By the way, meanwhile, we have a great question on YouTube chat. So what's the difference between K-means and nearest neighbor algorithm? Frankly speaking, I never used nearest neighbor algorithm, so I cannot answer live. Maybe Dmitry can, but if we can't, we can meet later on Discord and discuss that. That's for sure.
Yeah, let's leave it to at least to the end of this session.
Yep, good. So let's move on then. Then how does that work on the higher level, let's say? We will see it step by step on this learning workflow, which takes as an example any supervised algorithm, because for any supervised algorithm, it will work like that. Preparation, data split, training, and prediction. Let's take a closer look. First thing we have to do is to convert raw data into data with features and labels. What exactly that means? Imagine you have 1,000 of different emails. Those emails, by default, just a raw data, because no one knows is it a spam or not, and so on and so forth. So first thing we do is we go and manually mark up those emails with labels. That is a spam, that's not spam. That's spam, 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 not spam, 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 spam. At least that's how it was before, right? Then that will be the data already with some features or labels, prepared data for to train our model. When we split these data into three parts, bigger part, which is a training set, we will use it to train our model. Validating set and testing set. Validating set we will use to configure change settings for our model if it will be required, like we did with clusters for Kmeans. And testing set we will use to estimate our model if it's good or not. Then first thing we do is the training of the model based on this training set data. What is a model in this case? That's the model we create or machine learning creates based on the algorithm we decided to choose. And it's being trained on the raw data, prepared data. We will do it just like 15 minutes on the real data. Then we use separated validating set to tune this model to show, to see like maybe everything is good, but we may need to change some settings for this algorithm, amount of clusters, some more things. And then finally, when we think what model is done, we can estimate it with the testing set and decide if this model is good or not based on some metrics we will discuss in a couple of moments. And in the end, we export the trained model as a final model, and then we can start to use it to process new data, like new incoming emails. You've never seen them before, and predict labels for the new emails you just received to say this one is spam, this one is not spam, maybe. That's the general idea. Now, before we proceed to the lab, we have to talk about metrics, because you cannot control what you can't measure. Let's take a look at what are the metrics for us. We will explain metrics based on medical example or tumor example. Imagine a situation, we work at a hospital or with a hospital, and we want to help them identify malignant tumors to benign tumors. Let's take a look. We have 100 people under our supervision. 9 of them have a malignant tumor, which is very, very, very bad. That's deadly, basically. And 91 of them have benign tumor, which is, well, also not great, but not as deadly, not as bad as malignant tumor. The goal of our model is to identify those who are sick with a malignant tumor, who has malignant tumor, from those who have not malignant but benign tumor, which is not so bad. So we can arrange proper treatment, right? And we have a model which gives us some predictions. Let's take a look first about 4 fields we have here: true positive, false negative, true negative. Dmitry, could you please maybe explain us what's the true positive, false positive, and so on? For someone not into that, that sounds a little bit weird. What is a false positive?
Yep. So this table basically is called confusion matrix, and it represents. So it is divided as we have our model predictions on like columns, and we have true labels on the rows. That's like it generally is drawn. And true positive means that our model predicted a positive class, and it it is a true, so it is truly positive. And also, what we mean by positive? Well, very often a classification task is being conducted on the in the situations where we want to like find, detect, or classify some rare class among a huge amount of neutral class, let's say. So the neutral class is called a negative class, which we are not interested in, and the positive class is otherwise the class which we are interested in, and it's called positive. And so this table represents the number of samples which fall into different categories. So as I already said, the true positive means that the model predicts positive and it is really positive. The false positive means that the model predicts the class being positive, but it's not in reality, and so on. So I think you should get the idea of these definitions. And to be honest, a lot of skilled professionals, even through 3 years of their experience, they still misunderstand them. But that's probably normal because you don't often work with them.
Yep. Okay, good. So when true positive and true negative, we guess it right, our model gets it right, and false positive, false negative, our model guessed wrong. Now we are talking about metrics. So we are talking, there is a mention from Ronald Gaskin, sounds like we are getting into binary a little. And yes, indeed, because that's very simple classification situation. It's indeed very binary. We have 100 people, all of them are sick, and some of them are very bad sick, and some of them are just not so very bad sick. So yeah, it's a complete binary situation. You're right, Ronald. So why are we talking about this table right now? Because we want to understand how do we estimate our model, if it's good or not, if we should throw it to garbage or we can deploy it to production and change lives of our customers with it. Now, yeah, but for real, it maybe sounds a little bit too much, but it is for real. First metric you usually meet talking about any kind of model is the accuracy. Accuracy is a very simple evaluating metrics. It's very basically simple idea. Amount of predictions model identified correctly. Very simple. Accuracy is the amount of correct predictions divided by total predictions. In this case, total predictions 100 because we have 100 people. Correct predictions, so all true positives 1 and all true negatives 90 is 91. In this example, we have accuracy 91 divided by 100, 0.91. Understand what we cannot have accuracy higher than 1. Actually, usually 1 is unreachable height. So 0.91 looks very good.
And that's very suspicious if you get an accuracy of 100% or 1.
Right.
I would check everything, like that, double check everything if I would get a 100% accuracy.
Right. So now, based on this accuracy and your own personal experience, would you please write in the YouTube chat if you think this model we created is good or bad? What do you think? Accuracy is quite high. You can see it. Do you think this model is good or not so good? Just write it into the YouTube chat. Yes, good, no bad. I'm not sure. I see we have few dozens of people on YouTube, and that's amazing. So please just throw your opinion. Don't think too deep. We have to move on. But I want to see the overall opinion on that, if this model is good or wrong. Good or bad or not so good, not so bad, just medium, 50-50. Ronald thinks it's good. Any more opinions? Ksarambedkar thinks it's just good. Good. Okay. 3 opinions is enough already, but I will be happy if you will add some more. But at this moment, let's step back of our can be better. Okay, good, can be better. That's nice. Now let's take a look. Sometimes it's important to stop, step away, and think about what you are doing and why you are doing. That is amazing. Josh Turner just got my point, and Vincenzo is also very close to that. Well, yeah, actually not very close, but exact to the point, sorry. Not good for the purpose. There are many scenarios. Then this model will be good indeed. But don't forget, we are speaking about humans. We are speaking about people. Take a look at the amount of false negatives. 8 out of 9 people who have very, very bad sickness, potentially they are terminally ill. We are sending home 8 of them without proper treatment. So out of 9 very, very, very sick people, we just left 8 of them with no proper treatment. And that's quite a bad result. So the answer is this model is not just not really great. The right answer is from the treatment, from health treatment or sickness treatment point of view, we could have better result by literally throwing a coin. If we throw a coin, it will give us again yes or no results, true or false. But normally you have like 50% distribution on quite big numbers, right? So out of those 9 people, 4 to 5 will be identified as really sick with a very dangerous sickness. So having this malignant tumor. As a result, by literally throwing a coin, we would get better result than this model. And yeah, Catherine, we are getting there. That is very good. Very, very good point, Catherine. We are getting into the recall, or we are getting to the next slide. Let's call it this way. As you can see, accuracy is a great metric, but in some scenarios, it's not as useful. Do we have anything better?
Yes, we do. And yep. I wanted to point that in general, what is bad about accuracy is that it doesn't take into account the importance of classes that we have. So like in this case, we're talking about the situation where our positive class is more important to us, that we want to catch all positive classes, and we don't really care if we put that truly negative class to the positive class. But we do care about the opposite situation. And accuracy it doesn't care. It just measures the amount of correct predictions. So if you just want to catch like a single sample out of a large number of total samples, and like we would have an accuracy of like 99%, 0.99, and that's what accuracy would show. But if we were to catch that single sample and we wouldn't, then we failed. But accuracy won't show us that to us.
Right. So then we get to next metrics we can use to estimate our models. In this case, precision and recall. Those are a little bit different. Maybe you would like to tell us something about the precision.
Well, the precision is the number of truly classified positive examples divided by the number of the examples which model predicted as positives. And it's better for you to just think over and like let that definition like get into the depths of your mind. So just yet again, it's the amount of samples classified correctly as true as positive examples divided by the number of the positive examples which model thought were positive.
Yep. In this example, situation is very simple. Precision is amount of true positives divided by predicted positives. That means we have one true positive. We successfully identified one of them. And overall amount of predicted positives was 2. So one false positive, one true positive. So we have 1, 1, and one of them was correct. 1 divided by 2 equals 0.5. On the scale from 0 to 1, we already see what precision for this model is 0.5. It's definitely not good. Okay, then what is the recall? Recall, also known as sensitivity. Recall counts correctly identified positives out of all real positives. So we calculate here true positives, which was 1, you remember, to all real positives, which was 9, as you remember. And as a result, we have, for this tumor example, recall is 1 divided by 9, 0.11. So despite the high accuracy, precision is bad and recall is awful. That's why you never should measure your, well, in most of the cases, you should not measure your model based on one single metric, because our metrics may be not so optimistic. That's why people introduced, or data scientists introduced some, how to call it in English, composite metrics. May you say a little bit about that, Dmitry?
Well, first I wanted to point out that you can use a single metric, but what you should do that you should choose it carefully.
Right.
And if we're talking about the metric that combines precision and recall, that's called the F-score. And this is generally a harmonic mean of some values. It can be applied not only to precision recall. It's like a general thing. But if we're talking about like machine learning and precision and recall, that's equal to double product of precision and recall divided by the sum of these metrics, precision and recall. If we are talking that these precision and recall metrics are equally important to us, because there is a way of also weighting them in different proportions if one is more important to us than another.
Right. Okay. So, and one last point before we go on is the understanding of underfitted versus overfitted models. Take a look. I mentioned before what for the testing our model, we split some data, and we split the we split the prepared data we have into groups, 2 or 3, depending on if we do tuning for our model. And that is a very important point on what exactly is testing or estimating our model. The point is that there is a, if we proceed to talk about emails and classifying spam, not to spam, Then this testing set is a range of set of emails, what was labeled by human, most probably. Well, yeah, was labeled by a human, but never get to our model during the training process. Why is it so important? Take a look. If any of these emails get into the model, then it has a chance to train itself to be better fit. And as a result, when we estimate model using the same set of data as we use it to train, or they are partially mixed, like it may lead to very bad results. Our estimation will be very good because testing data got into training set, but this estimation will have nothing to do with the real life. So it's very important to keep training set isolated from testing set. Testing set never get to model before we want to estimate this thing. Now, why I'm talking about that right now? That's to explain underfitted to overfitted models. Underfitted model which didn't get enough data during the training, like that will be a common case when you try to train your model based on too small amounts of data. It will maybe catch the general idea and it will try to draw you a line somehow, but the real life values will not look like this line, right? Underfitted model give you too general results. It's not accurate, it's just too simple. It's not much the situation you want to describe with that. Then we have good fit or robust enough model or well generalized model. It means what if they have values distributed like that, and we are trying to draw a line, it will also go with them. Remember what idea of that is not too much literally every point of our function, but to keep as close to it as possible, to all of them as possible, to be able to predict next one. And when final, yep.
Yeah, I mean, if we were able to like find the exact function that would describe all these points, then we would go with just classic programming and write a function and just process our data. But
Yeah,
in
right.
machine learning, we work with approximating data, so we never get the like exact underlying function.
Yeah, perfect explanation. And then finally, we get to overfitted model or overtrained model, which will behave perfectly on trained data, but as it's not general enough, it will try to guess and try to catch each and every point. And as a result, we will have some very weird behavior which won't match into the real data. Okay, now with that said, speech is silver, practice is golden, or talk is cheap, show me the code. Let's take a look at the code and see how it works in a real life situation. Few words about tools we are going to use today. First, take a look. When you work with small amounts of data, you can use your own laptop and be happy. The problem is, as we discussed it above, if you use small amounts of data, your model doesn't have chances to be generalized enough. It will be underfitted. And if you want to train your model on the big amount of data, then your laptop will be very disappointed. And you will be disappointed ever more because it's going to be just too slow. And here comes Apache Spark. What is the Apache Spark? It's an open source, general purpose cluster computing framework, and it's distributed. What does that mean if we are trying to explain complex things in a simple way? It allows you to run computations over multiple servers at once, the same set of computations. Like making it very simple, it takes all of the computations you have to execute, split them into groups, give them to different workers, collect the results, bring them together, and give back to you. If you want to compute simple formulas, simple algorithms on a small amount of data, you obviously don't need it. But if you have data of a big company's size, imagine the amount of customers of Apple, amount of customers of Netflix, Spotify, and so on. Obviously, there is no server in the world able to train models at this size of data. Then tools like Spark come into the game, splitting those computations and executing them on multiple worker nodes. For our case, we will use Apache Spark machine learning feature, which allows it to work with machine learning algorithms, of course. Next tool we are going to discuss is Apache Cassandra. It's, as you could guess by the name, also delivered to you by Apache Software Foundation. And it's an amazing database, which is also free, open source, distributed, also decentralized NoSQL database, designed to handle any amounts of data. For example, Apple uses Cassandra to store the literally hundreds petabytes of data, not gigabytes, not terabytes, but petabytes. But meanwhile, keep this data in the fast access. It's not a cold storage, but it's an extremely quick database. It splits data into different partitions, into multiple partitions, and spread them over multiple servers. Also using clusters, of course, as Apache Spark does, but it does not for computations, but to store your data. There is a very important point. If you want your model to be good enough, you need to use a lot of data, and sometimes a lot of data just does not fit single server by the volume. In this case, we go with Cassandra because Cassandra splits it into partitions and store on multiple different servers. And if amount of your data grows, you can simply add more servers into your Cassandra cluster, and it will redistribute those partitions to the new servers automatically. One last feature of Cassandra I like also a lot is what one cluster, single cluster, can consist of multiple data centers storing your data in Europe, Asia, in the United States simultaneously, all servers as a part of a single cluster. And of course, everything is replicated multiple times, each piece of data stored multiple times. So even if you completely lost, for example, United States data center, I don't know why, but if you watch Hollywood movies, there are always some aliens, shark attacks, and whatever. So let's say we have lost United States data center, you will still have your data untouched in Europe and in Asia. So your application can survive a complete data center loss. As you could guess, it's a good fit for big distributed data sets. Then Jupyter. Jupyter, in our case, Jupyter Notebook is an open source web application which allows to create and share documents that contain live code, equations, visualizations, and so on. It uses mostly for data cleaning and transformation, some simulations, statistical modeling, and for us, first of all, for educational purposes. You will use this Jupyter soon, and you will see how it works. Last point in my list is a DataStax Studio. It's a developer tool to work with Apache Cassandra. To work with Cassandra, we use Cassandra query language, which is designed to be very similar to SQL. And DataStax Studio supports SQL, and we can work with data storage in Cassandra using DataStax Studio. Then a few more things. Dmitry, would you please?
Yes, we will also use some classical tools which are common in the area of machine learning and data science. This is, of course, Python language, which is an interpreted language, very simple to understand, very easy to read, and has a lot of support from built-in libraries as well as a lot of third-party libraries, which extends its capabilities like probably none other language can provide. We'll also use some tools developed, well, maybe not for exactly for machine learning, but which come in handy when it comes to machine learning. So one of them is Pandas. Pandas is a library providing a lot of methods to work with tabular data, which is a basis of like classic machine learning, where you work with tabular data. Another tool is PySpark. PySpark is a tool which allows you to work in Python while still using the Spark, all the advantages of the Spark framework, because the Spark initially is written in not in Python. I believe I've used Scala with Spark, but I don't know which main language is the basis of PySpark.
Frankly speaking, I don't remember. I believe it's Java. It should be Java.
Yes, probably,
But
because
it supports Scala as far as I remember, yes.
Yeah. So, but at least not Python. And PySpark allows you to write in Python and use all Spark advantages.
Yep.
Another common package is NumPy. NumPy is a package for like numerical and computations, and it's very fast. It uses a lot of C code under the hood, and Python does so as well, but maybe I'm not sure. Maybe not as much as NumPy does, but yeah, it's very fast, and it allows to do computations on arrays of data. And last but not least is the scikit-learn package. It contains tools to work with statistics and machine learning methods. So it allows for analysis of data, and yeah, it's a very common package in machine learning, classical machine learning.
Right. Good. Thank you so much. Now, about the environment we will use. Doesn't matter if you use your local Docker deployment or if you use our cloud instance. The idea will be the same, but you know what? Please do not use this link because the workshop content has moved. I will give you a new link. My bad, I didn't update it, of course. DataStax Academy. Academy. Going to be machine learning workshop online. Right. This one. Oops. And there is a Diogo Ibar asks if there will be another session for this one. Take a look. This one will be or is being recorded right now, so you can watch the recording and do your homework, do your lab afterwards. So don't worry, and you can ask us questions at Discord. So don't worry, you are not too late. So here is the link to the lab. Now let's go. What will be here? As a general source of storage and computations, we will use DataStax Enterprise, which unites Spark and Cassandra. It includes Cassandra with some advanced DataStax tweaks and analytics engine delivered mostly by Spark. DataStax Studio we won't use too actively today, but what we will use is Jupyter Notebook to walk through all the operations, all the procedures we have to do to train our model. And yeah, discussed already. Good. First lab we will do uses naive Bayes. It's a supervised classification algorithm. As we discussed it in the beginning, Wiki is not really useful when you try to read something about all those algorithms. Yeah.
You're trying to understand something, and you're still getting more and more puzzled by these definitions.
Yeah, when trying to find answers on Wiki, I usually find more questions than answers.
Yes, exactly.
Right. As a result, trying to find a simple explanation of how naive Bayes algorithm works, I will find out myself 6 years later with PhD in something. Uh, only then maybe I will get the idea of what's going on. So don't try to read that. We will find some better explanation. But what you need to know is naive Bayes is a popular method for text categorization. The problem of judging documents as belonging to one category or another, for example, as spam. Let's take a look better on how it works step by step as we did with Kmeans, and you will see how it works. Speaking of Wiki, sometimes funny comics will be better explanation than Wiki definitions. So let's take a look. That's actually a very funny one when you get it. Statistically speaking, if you pick up a seashell and do not hold it to your ear, you can probably hear the ocean. We have people from all around the world, so I have to explain this point. There is kind of joke or believing what in the seashell you can hear the ocean in it if you put it to your ear. I'm not really sure if it's like that or not, but that's a common believing. So, naive Bayes operates with probabilities, and in this case, we will speak about the probabilities of email being spam or not on the following example. Take a look. Those all definitions were naive Bayes for scientists. We have only one scientist here, at least like next to me on the screen. I'm just a human. I prefer simpler explanations for humans. Let's take a look at naive Bayes algorithm for humans. Explain it step by step. What's the story here? You remember, we start with preparation of the data. And naive Bayes is a supervised algorithm. That means what we have to put some labels in the beginning. And as a result, we want to have model, a well-trained model, what will say this email is mostly probably spam, and this email is mostly probably not spam. Normally, those algorithms are trained on the tremendous amount of emails. Millions, millions, billions, I don't know, on the huge, huge, huge numbers. With that, they work the best. But today, for the educational purposes, we will train our naive Bayes with only 8 emails, and let's see if it will make a good result out of that or it won't. Let's take a look. We just got 8 emails to label them. Get cash easy. So those are subjects of our emails, okay? Get cash easy. Win money now. Greetings from Dad. Could you lend me money? It was easy. I miss you. Wow. Check your trip itinerary. Money transfer received. Okay, in this case, we will consider money transfer received as spam. It may be not literally a spam, but for this case, for this situation, we will consider it as spam. When we label those money, label this money, these mails, those simple mails as spam and not spam, and 3 of them getting to spam folder. Money transfer received, get cash easy, win money now. And 5 of them get to not spam, will go to normal folder. Greetings from Dad, could you lend me money? Uncle, I'm tired of that, please stop. It was easy, I miss you. Check your trip itinerary. Okay, first action is done. Our data is labeled. Very, very well. Let's take a look on what's happening next. Give me a second. All right. So we have this very simple 8 emails only database, data set. store it in some database, for example. And we have to train using that. We trained our model using naive Bayes algorithm. Let's see how it will work for the new email. We just got a new email. Easy money. Subject is easy money. Is it spam or not? We have to answer this question. How human would ask this question? What is the chance it's spam if it has subject easy money? Or how would scientists write it down using this notation? What's the probability? So P, what it's spam given it has subject easy money. Notice what those are separated. That's not a single string, but two different words. That's right, we split subjects into multiple parts to prepare for that. Now, first step going live. Very stupid step at first, but later you will see how it works all together with all the others helping them. Without even analyzing subjects, what's the probability what email is a spam based on the data set we already have? Without reading any subjects, it's going to be 3 out of 8. That's very interesting point. Let's move on. We will get back to this point later. When we analyze those words, each one separately. First, let's take word money. Let's take a look. Money, 2 out of 3, word money contained in 2 out of 3 spam emails. First one and second one, so we have 3 spam emails, and 2 of them have the word money. So probability of the email containing word money, what it's spam, probability of the email which is spam to contain word to have word money is 2 of 3. When we do the same calculation for emails, those are not spam. Let's take a look. Out of 5 not spam emails, only 1 completely legit had the word money. So we take it. Probability of the email to have word money if it's not spam. On the right side, we have given fact, and on the left side we have probability. Is 1 out of 5. Only 1 email out of 5 had the word money. We do the same analysis for the word easy. By the way, yeah, it should be easy. Good. Out of 3 spam emails got the word easy, and only 1 out of 5 not. Now we think a very simple idea. It's a conditional probability. Email can be or spam or not spam. There is email cannot be half spam, at least for our purposes now, okay? So we use this very important idea to understand probability of email to be spam plus probability of email to be not spam is always equal 1. It cannot be 1.1. It cannot be 0.9. It's always 1. And now we start to calculate a very interesting idea. We calculate overall probabilities, we bring them together, map them together. So by itself, we cannot decide based on one particular probability if this email is spam or not. But combining them together, we are already getting somewhere. So take a look. We have, let's take a look at this row. Probability, what spam email has word easy, 1 of 3. Let's see. probability of a spam email to have word money, 2 out of 3. And overall probability of an email to be spam is 3 out of 8. And second step, we do exactly the same work, but calculating probability of that to be email to be not spam. Probability of a not spam email to content to have word easy, 1 of 5. Probability of not spam email to have word money in subject, 1 of 5. Probability of an email to be not spam at all, 5 out of 8, based on our data set, right? Very limited data set. Now we just calculate those values. Very simply, 1 of 3 multiplied by 2 of 3 multiplied by 3 of 8, it will be 1 divided by 12. We calculate the same for the probability email not being spam, and then bring them to the same, what is it in English? Divider?
Divided by?
Yeah, divided by the same value. And as a result, as we remember, what probability of email being spam plus probability of no email to be not spam is always equals to 1, we bring that to the situation what, based on our data set, probability of email to be spam, based on words easy in money it has in the subject, is going to be 0.76 or closer to 76.9%. And this decision mostly probably shows us what this email is spam, and we just trained our model on literally 8 emails, so the very, very, very limited data set. Normally we work with much higher numbers. Okay.
Lots of numbers.
Yeah, a lot of numbers, lots of numbers.
It can be hard for people not familiar with the basic of statistics, because this method is mainly based on the Bayes theorem, and this is more like more general idea of statistics, maybe not machine learning itself.
Yeah. So you see, I don't believe, I don't think you should get it all from the first scratch. No, I want you to get the general idea. And 2 points here you have to remember for this one is what the sum of probabilities in this classification is always 1. There are no chances it to be something third, because we have only 2 categories, spam and not spam. And then second point, what combination of multiple not connected points, why not connected, I explain on the next slide, can bring you to the very interesting mathematical results, what even a pretty simple model gives you very high chance of this email to be spam, and we're not even touching the content of the email, just subject. We don't have much time. Maybe you want to add something to this example, or we can go on?
No, I mean, what I would want to add is explained on the next slide. So.
Okay. Then feel free to explain next slide then.
Well, I wasn't prepared for that.
Okay,
well,
I can.
We discussed the. I'll try to. We discussed the Bayes algorithm, but there is also one word in the name of it. It's naive. And why is it naive? Well, it's because when we are discussing the relations between the features, and the features in the examples were the word money and the word easy. When we discuss these features, we make an assumption, a very strong assumption, that these features are independent of each other. What this means is that we are assuming that these words in the sentence, they are not connected with each other, and they can follow in any order, they can be in any place of the sentence. As you can probably know, that this is not always true, and you can see an example of that on the slide. Like after the word happy, there is a higher probability of meeting the word birthday after this than some other word. Well, maybe most of the words. And this is also true for many other phrases, which consist of several words. But the naive Bayes algorithm assumes that the features, which are words in this example, are independent. And while this is a very strong assumption, it allows for very good results in a lot of applications.
Yep. The idea may look stupid, as it, I believe, very well shown on the right side of the slide. It cannot be warm or cold outside at the same time. If you have the answer to question if it's warm outside, you already can assume what it's not called. For naive Bayes, it's not so obvious. And in the real life, words are chained into the phrases. If I say long, long ago, you can proceed with me in a galaxy far, far away. Every word or every feature in these are chained to the previous one. In a galaxy far, far away, every next word follows because we just know this quote. And naive Bayes will ignore these
Connections.
Connections, yeah, connections, well said. It will ignore those connections. Quite surprisingly, it's not bad. It's actually even good. For example, as we consider those facts or features as isolated, we can easily separate or parallel, spread it into multiple different tasks and run these, as we discussed it, for parallel computing. Then different tasks can be executed on different servers, different machines, which can make naive Bayes very, very fast, which also we want to have it fast, of course. Good, but we're still talking, and it's time finally to push some buttons. So, when you will deploy this Docker on your Docker, or if you will use our cloud instance, you will have something like that. And I will go for naive Bayes algorithm to show how it works in our case. Good, and kernel ready, so I can start. Okay, sorry, just a second. So output clear. Good. If you never have seen Jupyter before, don't worry, you will see how it works, you will get it. So what are we going to do? We are going to do two things. First, we are going to answer questions. Can naive Bayes be used to classify wine's rating score by its attributes? And meanwhile, we are going to try to estimate different wines our vineyard produces, because we have limited marketing budget for the next year, and we have to pick the best candidates, what mostly probably will be the best, so our marketing campaign will succeed, and we won't try to advertise worst wines, but we better advertise the best wines, right? So to put our budget allocated properly. How do we use Jupyter Notebook? I simply push the run button in the every cell what has to be executed. And first two cells are very simple. It's Python, and we are importing libraries we are going to use. We will use matplotlib, pyplot as PLT, and we will use some more libraries like pandas, a library to work with Cassandra, a library to work with PySpark, and so on and so forth. So we will use them to work with the data. And finally, most importantly, we will use PySpark for machine learning algorithms and classifications. We will import naive Bayes. Multi-class classification evaluator we will use to estimate our model, if it's good or bad. And some more things we will need to prepare data as we are going to work with it. Next step, we will define a function, show data frame. It's not really required, but it will help us to get data in nicer, more structured way, so it will be easier to read the data we are working. Well, and now we are ready, so we can start. First, as we considering a real-life world example, we will work with Cassandra. Cassandra is often used for big sets of data. So first step, I will create Cassandra cluster connection and connect to it. All good. Now, Cassandra stores data in tables, and every table must belong to at least one must belong to one key space. So in this case, I will create a key space. It's a Cassandra query language. Don't get too much into that. On the place of Cassandra, it can be any other database or just data loaded from file, from CSV file, for example, like we will work. And finally, I set this key space is active. If you don't have previous experience with Cassandra, it may be not really clear what's going on. For now, it's not matter. Then finally, we will create a table for vines. And let's take a look what are the qualities or what are the features of the vine we will consider. There are 12 different columns. Fixed acidity, volatile acidity, and so on and so forth. Chlorides, free sulfur dioxide, and so on and so forth. So mostly chemical values. Alcohol containers, and finally quality. First columns represent data we got in chemical lab. Every wine contains some alcohol, contains some chlorides, and so on and so forth. But last metric is very interesting. It's a quality. This one was given by some human wine experts as they find this wine good or not so good. What's the quality of this wine from the scale from 1 to 10? And we are going to load wine data set, which will be bigger than 8 kind of wine. Let's take a look. We will load white and red, and we will load them into Cassandra. So as you see, Cassandra query language looks very similar to SQL, which makes our life much easier. And I will execute this cell. It takes some time. You can judge. Okay, as you see asterisk, it means this cell is running. If you see the number, it was executed already. Okay, no mistakes, means data loaded. We can, meanwhile, proceed. And as data loaded, now we want to work with Spark. Now data is available in the database, and we want to work, when we want to use Spark to work with that. First thing we do is we create a Spark session. Very simple format in this case. We will use Spark Session Builder for the app name demo. Well, doesn't matter. Master will be local one because it's all launched together, get or create. Not so important. And then second thing already matters a lot. While this cell is being executed, let's take a look. That's going to be my Vine data frame. Data frame is a set of data we are going to work with. And here I tell Spark to read data from a database using format or Apache Spark SQL Cassandra. So reading data from Cassandra, thanks to DataStack's Spark Cassandra connector, by the way. And when we specify what are we going to read, we are going to read table wines, and we are going to use the key space we created before for this data, final comment load. It takes some time. Then finally, 2 prints. First print just table wine row count, and then finally how many we have rows in this data frame, wine data frame. We see it's almost 6,500. We can ask our function to show part of this data frame just to see how it looks. And we see it's a very simple table. ID of the wine, alcohol, chlorides, citric acid, and so on and so forth. Quality from 1 to 10, and some other chemical values. First, we want to simplify this setup. We don't want to train our model based on the bad vines. We want to focus on the good vines. Maybe it's a mistake, but this way we simplify data frame, make it smaller. That makes the training faster. We will have less data to consider. So here we go. We will create a new data frame, vine 6 data frame, based on the previous one, full, but we will filter, setting quality to be higher than 5. And now we can take a look, show data frame, vine 6 data frame. It looks exactly the same, but the only point is here we have had a quality of 5 and lower, and here we always have quality of 6 and higher. Never 5 or anything worse. Good. So we simplified a little bit of our work here. Now we will we will collect a vector assembler for this set of features. As an input columns, we will use the features we have, the chemical features we have, alcohol, chloride, citric acid density, and so on and so forth. But no quality, because for us in this case, it's not a feature, but the outcome of those features, right? And they will be collected as features. We, with this assembler, we transform this data frame into the training data, which we will use to train the model. And then we create a label indexer with input column quality, output column label, and that will be the main thing for us to prepare this label indexer and for this data frame. So let's execute that and take a look. It's not yet the training, we are preparing data. Okay, now we see this data frame training data 1, which has label indexer already processed training data we have had based on this vector assembler. And finally, then we print this training data 1 and count. We see first what we have 4,000 now candidates. Why? Because we dropped all low quality vines. That's clear. And now our data frame has more. So we still have ID, alcohol, fluorides, and so on and so forth. But now we also have features prepared for it. And we have label. Yep. Now, as discussed, we need to split our data set into training and test set. We won't do tuning, so we don't need split it into 3 parts. We will split it into 2 parts. And here we do those splits. Training data 1 will be randomly splitted in the proportion 0.8 and to 0.2. So 80% will go to the first split, 20% will go to the second split. And could you please remind me, this value is a random seed, I believe, for splitting.
Yes, exactly. It is needed to be able to reconstruct the experiment. So in case you need to like check what went wrong, you have the ability to split your data in exactly the same parts. So the same samples go to the same parts, namely train and test, as in previous runs.
Right.
So you.
Okay. Yeah, thank you so much. That's a very important point. So when we execute this split, we will see what train data frame row count has 3,000 and something vines, and test data frame row count has 700 for 47 vines. Now we have prepared data and split data. Now finally we get to the training of our model. First of all, we create this naive bias model based on the naive bias class from, as you have seen, one of the imports we did before. So it's a part of PySpark machine learning library. Let's get back. Right here. And here we define some things, some values we won't change, but those parameters or settings for this model we can change in order to try to improve the results. It will be model type multinomial. I'm afraid we have no time left to explain those parts, and smoothing of one. And we will train this model, then get the predictions with model transform on the test. You remember the test data we prepared before, and show those predictions. So I will execute the training. It was quite fast because, well, amount of data is not so high. And we can see we have some labels marked for the vines we have here. So we can go for show data frame predictions and show only qualities we are interested. Quality, label, prediction, probability. Good. And now finally, we can use multi-class classification evaluator to evaluate the accuracy of our predictions. Only accuracy we will get in this point. And we create this classification evaluator with label column label, prediction column prediction, and metric name accuracy. When we evaluate our set of predictions and print test set accuracy. Test set accuracy is going to be quite low. As we remember, it's not the only metric, but it may be also important metric for us in this case, as this case is different. We can try to replay this game and to retrain this model, changing the parameters. But we have only 10 minutes left, and I want to go on to the next slide because we gonna work with the same set of data using another algorithm. Take a look. This process is an iterative process. Maybe we chosen the wrong algorithm and we may find something better for our purposes or not. Let's take a look at the next one. Let's take a look at the random forest. I really like this name, by the way. Random forest sounds a little bit funny, at least for me. And random forest is a supervised classification ensemble method. What is the method and why it's not an algorithm, why it's ensemble method? You will see in a moment. As always, wiki is very useful. No, but before we proceed with a random forest, let's talk about the decision tree algorithm, which is an algorithm, not an ensemble method. Decision tree is a simple representation for classifying. Assuming what all of the input features have like simple answers, simplifying that, and there is a single target classification, and each answer has some reasonable limited amount of questions, we can try to build a tree of decisions giving us the results for something we want to predict. On the right side of this example, you see the Titanic survival decision tree, also one of the canonical examples. You can see if we want to calculate someone to survive or not to survive, a probability of that. And building a simple decision tree, we can try to ask those questions and base it on the answers, ask following questions, walking through features of something or someone, in this case, someone, getting the results. And the features used for this decision tree for Titanic survival percentage rate or prediction rate, let's say, we will use a very simple set of features: gender or sex, age, and amount of siblings, because surprising enough, it matters in this disaster scenario. And then based off the results, because it's a supervised method, so we can label. We know how many people died and what were the features, let's say, forgive me this comparison. That will be simple decision tree based on sex, age, and amount of siblings for this person. And this decision tree iterates through different features in order to calculate the probability for something. For example, if sex male, if age smaller than 9.5, if siblings count is more than 2.5, we get to this branch as a result. Oh, sorry. Yep. But if age is bigger than 9.5, we get to this branch. At these points, questions are stopped because we already know the answer, the highest probability in this case. That's quite interesting and simple methodic.
In general,
yep.
if any of you are more familiar with classical programming, this decision tree can be represented as a set of if-else constructions. Yeah, so the conditions are in the nodes, and the other if-else constructions or exact actions or exact labels are in the leaves.
Yep. But if you are going to write a decision tree manually, you are going to write quite a lot of them. For us, good side of a machine learning is what a model is going to create them, estimate them, and drop those what are not good enough. And now, interesting point. Decision tree is a great idea, but it's rarely used directly as just a decision tree. The problem of it is it tends to be very overfitted, trying to guess all the points when you use just the decision tree. And as a result, we get to the random forest ensemble method, which gets multiple different decision trees. Those are trying to give you the same results, the same predictions, based on different features. As a result, we solve the problem of overfitted model, making it more general, because those decision trees are random or almost random. There are different settings we can have. For example, some decision trees may have higher weight than the others, and there are some different points maybe applied, but the general idea is we get a lot of different trees, and we use combined result as like two decision trees say yes and one decision tree says no. It means for us what the result is 66.6% for it to be true if every tree has the same weight. Obviously, normally we have not the three trees, but much more, because normally we work with much higher numbers of features. So again, talk is cheap, show me the code. Let's switch to the next algorithm. Let's switch to a random tree with the same data set. Remember, our test set accuracy was 0.6. And one more thing you have to remember, when you just quit the notebook, its kernel, it's not shut down by default. So if you have not so powerful laptop or not so powerful cloud machine, if you will ask me for a cloud machine, Don't forget to shut down your kernels, otherwise you will simply run into no free memory issue. Now kernel is shut down, no kernel, and we can switch to the next lab. And this one will be, as you could guess, random forest. Same data set, we are still solving the same problem, but now we are applying a new algorithm or ensemble method to try to answer our questions. What are we trying to learn from this data set? We are still trying to predict wine quality, and meanwhile, we will try to answer a question, can random forest be used to classify a wine's rating score by its attributes? Beginning will be exactly the same. I'm importing libraries I need to work with this data, and as I use the new kernel, I will again define this function, same function just to show our data. I will have to connect to DataStax Enterprise or Apache Cassandra in our case, create the key space, use this key space and create table, same table as we have had before, and load data. Same data set as I said, 1, 2, 3, 4, 5, 6, 7. It's going to be there, yes, in a moment. This step, again, will be the same. We have to create a Spark session and read the wine data frame from Cassandra. It takes some time, but now we are done. And we can take a look. We have the same table and same vines with the same data. Basically, we use the same files to load the data. This step must be familiar to you already. I'm filtering out vines with a bad quality to focus on the vines with a high quality. Now I'm getting the same vector assembler. And basically, this step is more or less the same like we did before. So I won't explain it again. These all may look a little bit too much, but it's an overview level workshop. Don't feel sad and bad if you didn't get it all from the beginning. I want to show you an overall picture on how it works, answer your questions in the end, and then if you are interested, we will maybe suggest you some ways to get more data about that. Maybe in the result, you will become a data scientist. No, Dmitry needs some colleagues.
I definitely do.
Yeah, this job is in high demand, and this demand will only grow. So if you will decide to become a data scientist, and you will become at some point, please let us know if it was just like a consequence of this workshop. It will be an amazing feedback. So we have this training data prepared. Now we do the same split. We still need train data and test data. So it's still the same numbers because we, well, quite expected. Now we get to random forest classifier. Our label column, well, will be label. Features we use to make decision trees will be features. So those we prepared before. You remember with those vectors. And finally, we define the number of trees we need to have. That's a very interesting point. When we execute the training, we create those predictions, and let's take a look what we will get as a result. Boom. Okay, 747 predicted that the test data, at least we didn't have quality for this several during the training. We are now trying to predict what it will be. Now we can show this data frame with predictions, showing quality, label, prediction, and probability. And as you could guess, we can use multi-class classification evaluator to evaluate accuracy of our predictions. And now test accuracy is not 0.6 like it was, but closer to 0.7. Looks like accuracy significantly changed. That's quite an interesting point. because changing the algorithm, doing the same steps with the same dataset, we already got different results. Very much makes sense. And you know what? I'm not an expert in this field in no way, but I know I can play with those values. In this case, I want to change num3s. First try to raise them, then tries to decrease them. Dmitry, what would you guess? Will it change the accuracy or not?
I think it will.
Okay.
But I'm not sure in which direction. But depending on how much you will change it and in which direction you will change the number.
Yeah, makes sense. So
then
don't
probably
forget.
I can make assumption.
We have 10 different or around 10 different features in these features columns. So first, I will try to decrease the number and set it to 3. I will execute this cell again. Boom. Very well. I may show it, but it doesn't really matter because what we want is to evaluate this model. And accuracy decreased, but actually much less than I expected, but it decreased. That's interesting. And if I will try to set the number of trees to 1, like it cannot be less than 1, in the forest you cannot have less than 1 tree.
Yeah, and we are getting just a single decision tree in this case.
Right, so I'm kind of excluding, is that right? I'm excluding random forest and I'm working with a single decision tree in this case. We will.
Yes.
Yeah, and take a look. In this particular case, result even improved. That's interesting. And I will try to raise this number. What should I try? What do you think?
Yeah, try 20.
20?
Probably.
Okay, let's try 20. Run.
You've had 10 already, so just doubling the number.
And I will re-estimate it. Okay, 0.7, not bad. Already better when it was with 10. But what if I try to go, let's say, for 100? I have no idea if it will improve the result. But now we can take a look on what accuracy will say. And accuracy actually decreased. As we have seen, too much is sometimes also bad. Okay, so we tried to tune our model. And it looks like we are getting different results.
Yeah,
science, guys.
We should also mention that there are a lot of other parameters to that class, and we can also change the depth of the tree, the maximum number of leaves that are coming out of a single node, and there are just many other parameters that can affect the results of the evaluation of the model.
Yeah, I'm afraid we are already 5 minutes out of time. So what we suggest you, as we invite you to follow us, and do this work, then that's going to be for you to experiment. Read the documentation on random forest classifier, which is a part of, I believe, PySpark. Random forest classifier, right. So in the PySpark documentation, you can find other options for random forest classifier and try to play with it and surprise us by your raising accuracy. As you know already, accuracy is maybe not the most important metric, but it all depends on your particular case. That brings us to the last few slides. We will answer questions in a couple of minutes. So last slides. Don't forget, this Wednesday, we built a multiplayer game with real-time interactions using event streaming. It's prepared by my colleague Stefano Lottini, and it's an amazing one. As an insider, I've played this game already and built it, and that's a great job. So I do suggest you to join and make yourself familiar with event streaming. And next week, next Wednesday, we build an appointment scheduling app using Spring, WebFlux, and NoSQL database. Spring means Java. So if you are interested in Java, that's definitely going to be a good place for you. And of course, NoSQL is very important for anyone who wants to be a good engineer to understand. Okay, final point. To run it locally, use the link we have sent already, DataStax Academy Machine Learning Workshop online. For the cloud setup, contact me. I will put it again. I believe you already did, datastax.io/Alex. I will be happy to help you with that. And if you have any questions, find us on Discord. One last point. DataStax is well known for its support development of Apache Cassandra, one of the best databases in the modern world. But Apache Cassandra world has one big problem. It needs you. The story is world need more qualified engineers with experience in Cassandra than it currently has. So our idea, we sponsor education and certification for you to become a certified, experienced Apache Cassandra developer or administrator. That means what you can get education in this field and certify you and pass the certification for free without paying a cent. First thing, to do so, you need to do two things. First, you follow this link, and where is my YouTube? Right here. You follow this link, voucher, to get your voucher, which will give you 100% discount for Apache Cassandra certification. Second one is going to be the place for you to get ready for the exam, because obviously you cannot do it right now. You have to prepare yourself first. Best place for it to prepare is academy.datastax.com, where you have free courses for that to get ready for the exam. And by the way, currently they are available only in English, but we work to deliver subtitles in multiple languages. Work has started, so hopefully over the next months it will be delivered and you will have multiple options. What matters for you the most? There is an administrator path or developer learning path. It's the best way. And there are also information about Kafka, connection to Cassandra, and so on and so forth. Good. So that must be enough for that moment. I don't wait for too long to get your voucher. The form will be closed after some hours. And thank you for visiting us. We will be happy to answer some questions, if any. There is a point from Messi. DSC cluster stops when running Docker Compose up, so cannot do the exercises in the notebook. So take a look. All these stat of the things we are using today is quite heavy. It's like production-like workloads. So if it cannot be executed on your laptop, especially if you use Windows or OS X, first check resources allocated for your Docker, because it's obviously going to require quite a lot of resources. If you cannot launch those exercises on your machine, you know what to do. Ping me on LinkedIn or via email, and I will create a machine for you in the cloud, which will have Linux and enough resources to execute those steps. Any more questions? Or we are done for today? Yeah.
I also wanted to address the question about the differences between K-means and K-nearest neighbors. If this is still relevant,
yes, sure,
then
of course. Please remind the question. First question was, what's the difference between K-means and closest neighbor algorithm, right?
Yes. So the difference is that K-means is obviously a clustering algorithm, and what it does is that it doesn't use label data to train the model, and it in fact it uses the training data to find those labels in some sense. So it finds clusters which are labels for our data. So it shows which sample belongs to which cluster. This is a kind of a label. So it finds those labels. And the k-nearest neighbors algorithm is otherwise is a classifying or a regression algorithm, and you have the labels at your training step. So you already know which label to which label belongs each sample. And so what you do is you learn the underlying function to do the same for any new data. So I hope that explains something.
Yeah, I think so. One more question was asked in the very beginning, but a really great question. Could you recommend any resources for machine learning, articles, books for beginners, and so on?
If there are any other questions, then proceed with them, and I will think and look for
No,
suitable
not in
questions.
the
I mean,
moment. Not at the moment.
there are a lot of sources, and it is really difficult to choose the best ones.
Okay, but we need at least something.
Well, I remember that Goodfellow's book is very good, but it's, as far as I remember, it's generally about deep learning. So if you need something about machine learning, like classical machine learning, and it should be in English. I can't remember any right now. Maybe if you can contact me in some way, I can.
You can
advise you
paste a link to your LinkedIn if you use it, or you can send
Yeah,
it
I
to
can.
me.
Yeah, wait a second.
Mm-hmm. Mm-hmm.
Here it goes.
Thank you. In a moment. Praveen Sahu recommends Machine Learning by Tom Mitchell. I can say what I took a machine learning course by Udacity. It was a great experience. So personally, I believe it was a great course.
Yep, I remembered. You know what? There's a great book by Bishop, I believe. I don't remember its correct name. Let me just Google it quickly.
Okay.
It's called Pattern Recognition and Machine Learning, authored by Bishop.
Yeah, pattern recognition and machine learning, Christopher M. Bishop, right?
Yes.
Mm-hmm.
This is a very great book and good for starting in this area.
Okay, let me send you a link. Oh, it's going to be an Amazon.de because I'm located in Germany, but I hope you can adjust this link to your needs. Pattern recognition and machine learning. Great. Okay, maybe this one. Yep. I believe there should be a newer publications. But yep. Okay, so if there are no more questions, we are done for today. I have to say many, many, many thank you with those dozens of people who stayed with us till the end. I hope we managed to show you the very fundamentals, approaches, and use cases. And now you can say if you are interested in this subject or not. And as I said before, if as a result you will get your job in data science field, please let us know. It's always an incredible feedback to know what people want, what people were interested, and made it till the very end. Thank you, VibeHub. Thank you for your gratitude. Um, if you liked it, please, there are the buttons right below Dmitry. Like and subscribe. We run a lot of great workshops on this channel, Data Stacks Developers. And of course, we will invite Dmitry again on other sessions to help us with. We're always happy to have external speakers.
Thank you. It was a pleasure.
Yeah, it was a great pleasure to host you here, and thank you for support. Thank you, everyone, for visiting. It was a great time together, and hope to see you on Wednesday. Have fun, and have a great week. It's Monday, so use this week in its full. Go do something great. With that, that was Alex and Dmitry. Thank you so much, and see you again later. All the best. A little bit of music for you in the end.